All right, lesson 1-3. Here we go. So infinite limits at infinity, and doing some graphing. So review, graph the function below. The graph of the function f at x here has a hole where, and to understand that is to understand where something is removable. So notice how x minus 1 is removable. So the 0 of what you removed, a little space here, the 0 of what removed is at x equals 1, because that's what got removed. Where is there an even asymptote? Where is there an even exponent? What's the 0 here? So it's positive 2. And where is there an odd vertical asymptote? Is when there's an odd exponent, so it's positive 4. Sometimes you got to be careful of the signs when they come out. In the graphs below, the vertical asymptotes are labeled odd or even. If they go in the same direction on both sides, it's an even asymptote. If they go up one way and down the other way, they are odd asymptotes. All right, turn the page. So you've seen examples where a limit doesn't exist at a vertical asymptote. Such non-existent limits can be expressed as infinite limits if the vertical asymptote is even, or if you're finding one-sided limits. So we're not just going to write down does not exist for these. So we will write these limits equal to infinity or equal to negative infinity. So the examples below make use of your knowledge of even and odd vertical asymptotes as well as holes. So if I look here, at positive 2, there's an asymptote. It's not removable. So to the right, pick a number bigger than positive 2, like positive 3. Recognize it's a positive answer, which means at that side it goes to positive infinity. So a fact about vertical asymptotes is on one side or the other side, they always go to infinity or negative infinity. So if you have a positive answer, then it's going to go to positive infinity. If it's negative, then it's going to go to negative infinity. So if I look at the same question here, but from the left, pick a number smaller than 2, like positive 1, and you'd end up with a negative answer. So on the other side, it's going to negative infinity. Here we have an even asymptote, so both sides are going in the same direction. So if you pick a number to the right of it, now at positive 2 is x-intercept. So if you pick like 1.5, not quite 2, so like 1.5, it's going to be negative, and to the other side of 1, like 0, it's negative and negative on both sides. So therefore, both sides are going to negative infinity. Again, if we have an asymptote, and that asymptote's at 1, then when I think of the graph of it, what's happening at 0 or what's happening at 2? Now, I didn't pick 2 because at 2 we have a x-intercept. So I picked a number between 1 and 2, like 1.5. Plug it in, I get a negative divided by a positive. That's why I know both ends are going down. And for an even asymptote, they go in the same direction. All right, same question here, but to the left, it's going down. And this question here, if I plug in 2, this one, be careful, because it's removable. So we have x plus 2, x minus 2. So this is removable, and then plug in 2, and the limit value is 4. All right, limits at infinity. So limits at infinity are really looking at end behavior. That's the key part here. And horizontal asymptotes really are end behavior when I look at it. So when I look here, can you find the horizontal asymptotes? That means power divided by power. So when I divide it, I get 5 over 10 or 1/2. Here again, power over power. Notice the bottom is more powerful than the top. So the horizontal asymptote is at 0. Here, power over power. There is no horizontal asymptote because the top is more powerful than the bottom. Number 9, find the following limits. Now, as x approaches infinity, we want to find the right end behavior. Now, this is exactly matching this above. So the horizontal asymptote tells you the end behavior. So if you go power divided by power, that gives you the end behavior. So this answer is 1/2. If I go power divided by power here, this answer is 0. Here, power divided by power, this one has no horizontal asymptote, so it does not exist. At number 12, this one's a little more challenging because it's not multiplied out. So I have to multiply it out. So it's 2x times x squared. Here it's x times 3x squared. Got to be really careful. So 2x times x squared is 2x cubed. Here 3x squared is 9. So that's 9x cubed. So if we don't multiply it out correctly, the x cubes divide out and you're left with 2 over 9. But you would only see that when you just look at the power terms and multiply them out. Make sure you consider the highest degree terms, not the highest degree factors. Exactly. So we're not looking at factors, but they have to be multiplied out. Number 13. Rational functions like those above have at most one. Sometimes they have more than one horizontal asymptote. So if I look here, what's happening as it goes to infinity? So still power term over power term. Now the square root of 4x squared is 2x. So this is 2x divided by x. So the right end behavior is going to 2. That's 2x divided by x. That's where that came from. But for the left end behavior, when I solve this and you put in a negative number, the square root here is going to be a positive divided by a negative. So the power term here is going to be negative 2. So if you think of the square root of 4x squared over x, when you take the square root like a quadratic, the answer could be positive or negative. And so you need to recognize the answer could be positive 2 or negative 2, what direction that you're going. Are you putting in a positive number or a negative number? All right, some graphing. So if I look at number 15, 16, and 17, I want to graph these. So first I want to be able to analyze it. What's the domain here? So if I factor out the denominator, you get x subtract 2. So the two numbers that x cannot be that make a 0 in the denominator are 0 and positive 2. Both of those values are restrictions. So x can't be 0 or positive 2. Why can't they be that again? Because it gives you a 0 in the denominator. The vertical asymptote. So neither one of these are removable. Both are vertical asymptotes. If it was removable, it would create a hole in the graph. And then the end behavior comes from the power terms. See if I can get, I know it got a little blurry there. And so if I look at the power on top compared to the power on the time. So identify the power terms. I want you to notice the bottom is more powerful. So therefore the end behavior for both, and we're going to write them, we can write this as just a horizontal asymptote, that the end behavior is 0 in both directions. All right. The domain here, what's the restriction? X cannot equal negative 3. It's not removable, so that is a vertical asymptote. And the end behavior here, we have 2x cubed, and on the bottom, if we multiply it, it's x squared. And then if I simplify it, the end behavior is going to act like 2x. Number 17, the domain, what can x not be? It's nice that they factored it. So positive and negative 2. If I reduce it down, x subtract 2 is removed, and I just have x plus 4 over x minus 2. Over x plus 2, I mean. So what remained in the denominator, that creates a vertical asymptote. So negative 2, that restriction remained, so it creates a vertical asymptote. What's the 0 that got removed? That's positive 2. When I plug positive 2 into here, I get 6 over 4 or 3 over 2. And then the end behavior are the power terms. So x squared divided by x squared, that's 1. So the end behavior is 1. All right, let's keep going. Give the domain reduce it down, find the asymptotes and intercepts and behavior, and graph it. All right, here we go. Number 18, the domain is all real numbers. There's no restrictions. We don't have a fraction. The x-intercepts are 0, positive 1, and negative 2. 0, positive 1, and negative 2. So 0, positive 1, and negative 2. The y-intercept, if I plug in 0 for x, I get the answer 0. And the end behavior, if I multiply it out, x times x squared, the end behavior is x to the 4th. So both ends go up. Here we go. So the right end goes up and the left end goes up. What else I know is if it has an odd exponent, it crosses. So at 0 it crosses, and at positive 1 it crosses. So we're going to cross, but at negative 2, it only touches and comes up. And that's because there's an even exponent where that 0 came from. So an even exponent means it touches. Odd exponents means they cross over. Number 19. This is a rational function. The domain are the values that x cannot be from the denominator. So x cannot be 0, cannot be positive 1, and cannot be positive 3. If I reduce this down, I'm going to do it up here. X makes x squared just an x. X minus 1 squared, and x minus 1 makes that just x minus 1 on top. X plus 3 and x minus 3, they don't simplify at all. Two different factors. So now it's simplified. That's this answer. Where's the vertical asymptote? What remained on the bottom? So x can't be 0. That remained. And the other one is x can't be positive 3. The holes, what got removed from the denominator? Notice this one, that's positive 1. And then you plug positive 1 here, and 1 take away 1 is 0. And so when I go multiply or divide, the answer is going to be 0. So at 1, 0, there's a hole. The x-intercept, look at the numerator. Now 1 is a hole, so the x-intercept from the numerator is negative 3, makes this a 0. I want you to also notice as an odd exponent, so it's going to cross. The hole also has an odd exponent. The y-intercept, put in 0 for x, and it's undefined. So there is no y-intercept because it makes it undefined. And the end behavior, the power terms. So if I look at the power terms, be careful. I could go from the reduced form. X times x cubed is x to the 4th. X times x squared is x cubed. So the end behavior is the line y equals x. All right, I'm going to draw something on here. Asymptotes and holes. So we have an asymptote at 0. We have another one at 3. We have, what else do we have? We have a hole at where 1, 0. That's right here. And we have slanted asymptote like y equals x. That's that right there. So there's the line y equals x. Now what points do I know? I have an x-intercept at negative 3 right there. And we're just going to go from there. There's no y-intercept. So let's start here. We know at one end that it crosses there. So it's going to cross over. So on one end it goes to infinity, it crosses over and goes to negative infinity. Here, it crosses over at the hole. And know that this asymptote, it has an odd exponent. That means on one end it goes up and on the other end it goes down. Same thing here. At this hole it crosses over the hole. It's okay it crosses here. And again, this asymptote is even. So on both sides it goes to infinity and then the end behavior. Putting all the pieces together and drawing your graph. Number 20. Last one for the lesson. Domain, if I look at the denominator, what values for x makes it 0 on the bottom? And you can see it's positive and negative 2. Makes it 0 in the denominator. What are the vertical asymptotes? Those are vertical asymptotes, positive and negative 2. Actually, we need to be more accurate here. I think it's better looking off the graph. So at negative 2 and positive 2, we have vertical asymptotes. I want you to notice that if you pick any number between negative 2 and positive 2, so if you put in negative 1, if you put in 0, positive 1, it gives you a negative answer under the square root sign. So that means the domain is less than negative 2, and the domain is greater than positive 2. So it's to the left of negative 2 and to the right of positive 2. There's no holes. X-intercept, negative 1 from the numerator, and it crosses over. But negative 1 is not in my domain, so that means there's no x-intercepts. There's no y-intercept. If you put in 0, you get a negative answer in the square root, so there's no y-intercepts. The end behavior, if I look at it, it's going to be the square root of x squared. So it's positive and negative. So if I think of it as positive and negative 1, so I'm going to do that. So positive 1 and negative 1, and then I need just to graph it. So if you want a sense of where to graph it, if I put in, you know what the asymptotes, what's it going to do? It's not going to be a negative answer. When you put in a positive answer, the answer is positive, and that's the end behavior. If you put in a number less than 1, it's going to be a negative answer divided by positive, so this is going to be negative, and the end behavior. A little bit challenging, right, to graph these. All right, there's your lesson on limits at infinity, infinite limits on graphing. Mr. G Math, I'm proud of you. And we'll do assignment 1-3.